So, let's talk about a classic coding problem. It's one of those questions that pops up all the time in technical interviews, and the solution is, well, it's just beautiful. How do you find a hidden loop in a massive list of data?
Okay, picture a giant chain of data, what we call a linked list. Each piece of information just points to the next one in line. Simple enough, right? But somewhere in that chain, it might secretly loop back on itself. Now here's the challenge. You have to find that loop, but, and this is the kicker, you can't use any extra memory. You can't make a list of places you've been. It sounds really tough, but the solution is surprisingly clever.
And that's exactly what we're diving into today. We're going to break down Floyd's cycle finding algorithm. You might also hear it called the tortoise and the hare, which honestly is a much better name. By the time we're done here, you'll know exactly how to spot a cycle, find its starting point, and even figure out how long it is.
To really wrap our heads around this, we're not going to start with code. Nope, we're going to start with a simple story about a race.
So imagine this. There's a long, straight road. This is the start of our data list. But this road doesn't just end. At some point, it merges seamlessly into a giant, circular racetrack. That circle, that's our hidden loop. We have no idea if it's there, where it starts, or how big it is.
Now, at the very beginning of this road, we place two racers. These are our pointers. First up, we've got our slow walker, the tortoise. Super steady, just takes one step at a time. And then we have our fast runner, the hare, who's way more energetic, taking 2 steps for every single step the tortoise takes.
All right, so they're off. They start moving down the road. Now, if the road is just a straight line, obviously the hare gets to the end first. No big deal. But what happens if they both end up on that circular track? What's the one thing that is absolutely guaranteed to happen?
You got it. The fast runner, the hare, is just going to keep zipping around that circle. And because they're moving twice as fast, they will inevitably catch up to and lap the slow walker. It's not a question of if they'll meet, but when and where. And that moment, the very fact that they meet at all, is our absolute proof that a cycle exists.
So that meeting is our proof positive. A cycle exists. But you know, just knowing there's a loop isn't quite enough to solve the whole puzzle. We actually need to figure out 3 different things.
We're going to tackle this in 3 distinct phases. Phase 1 is what we just did, detecting that the cycle is even there. Phase 2 is finding the exact front door to that loop. And phase 3 is measuring just how long that loop is. Let's make phase 1 official. We move our pointers, one slow, one fast. The second they land on the same spot, we stop. We've proven there's a cycle. On the other hand, if our fast pointer ever runs off the end of the list, if it hits a dead end or a null value, then the race is over, and we know for sure there is no cycle.
Now get ready for the most brilliant part of this whole thing. That spot where they first met, it's almost never the actual start of the loop. To find the real entrance, we do something that feels like a magic trick. You leave the fast pointer, the hare, right where it is at the meeting spot. But you take the slow pointer, the tortoise, and teleport it all the way back to the very beginning of the road. And now you change the rules. They both move at the same slow speed, one step at a time. The place where they meet for the second time is guaranteed the exact start of the cycle. It's amazing!
And phase 3? Well, that's just the victory lap. Once we know where that cycle entrance is, we just take one pointer, walk it around the loop, and count our steps until we get right back to where we started. That number, that's the length of our cycle. Simple as that.
Okay, we've got the story, we've got the logic. Now let's see how this beautiful idea translates into some really clean, elegant code.
So here's the code for phase 1, detecting the cycle. The most important part is that while loop condition right at the top. We have to check that fast isn't at the end and that fast.next isn't at the end before we try to jump 2 steps. If we don't, our program could crash. Inside the loop, it's just what we talked about. Slow moves 1 step, fast moves 2. And if they're ever the same, we found our meeting point and we can break out.
And here's the code for that phase 2 magic trick. We make a new pointer, let's call it entry, and stick it right at the head, the very start of the list. That's our reset. Remember, our other pointer, slow, is still waiting at that first meeting spot. Then we just start a simple loop where we move them both forward 1 step at a time. The loop stops the second they meet, and that spot is our cycle entry.
So you might be wondering, why go through all this trouble with tortoises and hares? Why is this algorithm so famous? Well, it all comes down to one critical idea: efficiency. The real magic here, the reason this is so brilliant, is its efficiency, specifically something called O of 1, or constant space.
All that means is that whether your list has 10 items or 10 billion items, this algorithm uses the exact same tiny amount of memory. All we need is space for our 2 pointers, and that's it. The memory use never ever grows, no matter how huge the problem gets.
Let's put that into perspective. A different way to solve this is to use a hash set. You just walk the list and you keep a record of every single place you visited. If you ever try to visit a place that's already in your record, you've found the loop. It works, and it takes about the same amount of time. But, and it's a big but, its space complexity is O of n. That means the memory it uses grows and grows with the size of the list. It's the very thing we were trying to avoid.
Okay, pro tip time. If you're ever in an interview and this comes up, here are the traps you need to avoid. First, forgetting those null checks for the fast pointer. It's an easy mistake that will crash your code. Second, and this is the biggest one, assuming the first meeting point is the start of the cycle. It's not. That's what phase 2 is all about. And finally, just be careful with your counting logic so you don't have a silly off by 1 error when you measure the length.
So if you only remember one thing from all of this, let it be this. This one sentence sums up the entire algorithm perfectly. 2 speeds expose the cycle, a reset and walk finds the entry, and 1 full lap measures the length. We've spent a lot of time on the how of all this, but that leaves one last fascinating question. Why does that phase 2 trick actually work? Why does resetting 1 pointer and moving them at the same speed guarantee you'll find the entrance? Well, it's not magic, it's just some really cool math. It turns out the distance from the start of the list to the cycle's entrance is mathematically identical to the distance from the meeting point back around to that same entrance. Proving that for yourself? That's the perfect next step to truly master this algorithm.